recently. So welcome, Mike.
Thanks. Yeah, good to be here. I haven't been to Maryland since I think 2015, maybe 2016, certainly before the new building. And now my wife works in Bethesda, so I kind of moved to the suburbs, and I live actually, I think, closer to here than to Hopkins.
Oh,
But yes, it's good to be here. Good to be back in a much nicer building than last time I was here. Yeah, so it's controlling towers on my ski rental with Sungjin, Thomas, Ben, and Sergey. Yeah, I did most of this work was while I was on sabbatical at Google New York. Yeah, so before I dive in, like I was kind of saying a little bit, I like doing theory seminar talks in general because I can, we're all theory people here. I don't have to, talk about other kind of stuff. I was also saying this is probably the first time I've written code in like 8 years, 10 years maybe. And so this is a kind of a fun project because the math here is, I think, very cool because it's very surprising, but very easy. And so like, I'm not going to show you any complicated techniques. I'm not claiming there's some great new kind of algorithmic idea here. What I'm going to claim is that really weird stuff happens that you wouldn't expect. I'm going to convince you of that with a bunch of graphs. Right? So I get to pretend to be an applied person again. And then I will, we'll throw up equations and do some proofs, but like I'll kind of hand wave it and skip through it probably pretty quickly. So that didn't want to work. Good. So probably most of you have seen the ski rental problem, but just in case, I'll do it from scratch. This is kind of the most basic problem in online algorithms. Right? So this is usually like when I teach undergrad algorithms and I teach one lecture on online algorithms, right? This is what you start out with. So it's kind of the archetypical example of rent or buy, which is kind of this large class of problems, and this is kind of the abstraction that lets us study all of them. Okay, so the story is, I like to go skiing. I want to go skiing, but I don't know how many days I'm going to get to go skiing in the year. Right, and so every day I can kind of go to the mountain. I can rent skis, and that costs, let's say, $1. Or at any point in time.
I want to know what ski resort you go to, by the way.
Okay, so I will say this is a much different conversation we could have because I'm originally from Vermont. So I refuse to call anything around here skiing. It's sliding gently down a hill. So let's pretend we're back up home in Vermont and we get to go skiing at actual ski areas. So I can rent for $1. Yeah, it's sort of normalizing, right, with inflation. Just add 2 zeros to everything if you want. Or I can buy at any point in time, right? It's not like I have to buy at the very beginning, right? I can ski some number of days and then choose to buy if I want. Or I can buy that costs more, right? It costs more to buy than to rent. And the problem is I don't know how many days I get to go ski. And if I knew ahead of time, oh, you're going to get to ski once, then like, of course I'm not going to buy. Right? If I knew ahead of time, oh, you're going to get to ski 10,000 times, right? Let's pretend a year is infinitely long, right? So you get to ski 10,000 times, then like, of course I'm going to buy at the very beginning. Right? The issue is I don't know that. Right, and this is, like I said, this is the most basic problem. It's very classical. So, like I'm at a theory seminar, I don't have to answer questions like, why don't we use past data and predict how many days it's going to be? And we'll throw a neural network at it and all this stuff. Like, we're not doing machine learning, right? This is online algorithms. Right, so, again, most of you have probably seen this, right? But you can kind of immediately see that two obvious things are bad, right? Like if I buy right away, no matter what, right, then I pay B. But the adversary gets to choose how many days I go skiing. Says, okay, you only get to go skiing this one day. Okay, so you pay B, the algorithm is B, the optimum is 1, so the competitive ratio, the algo over opt, is B. Okay, alternatively, if you never buy, I just commit, I'm renting every day forever. Okay, then the adversary says, okay, you're going to ski an enormous number of times. Okay, so then I pay M, which is much bigger than B. So my competitive ratio, algo over opt, is M over B, which is arbitrarily large. Okay, so these are bad algorithms. So we probably all know, or many of us know the classical solution, right, which is rent B minus 1 days, and then buy. Great, and the theorem is that this has competitive ratio equals 2. It's slightly better, 2 minus 1 over B. Okay, and it's a 2-line proof, which is why I can teach this in my undergrad algorithms class. Right, say, okay, if the adversary sets me up less than B minus 1 or less days of skiing, then I'm optimal, right? The optimum thing was to rent every day. I rented every day, so I did the optimum thing. If the adversary lets me ski more than B times, well, okay, what did I do? I rented B minus 1 times, and then I bought, so I paid 2B minus 1. The optimum thing was to buy at the very beginning, right? But I didn't do that because I didn't know. So I paid 2, so my competitive ratio is 2 minus 1 over b, so at most 2, right? Think of b as being very large. Okay, so we've probably all seen this before. What we may or may not have seen, I certainly didn't see until like semi-recently, which may be a little embarrassing. I don't know if you all have seen it, is that there's actually a randomized algorithm for this. Okay, this was not taught to me in my undergrad algorithms class. I don't teach it to my undergrads. But it turns out there's a kind of almost as classical, so basically at the same time, randomized algorithm. So we have to be a little careful here about powers of our adversary, right? We always have to do that when we have randomized stuff. Fine, so we'll say we're going to have some distribution P, which we call the purchase distribution, and we're going to choose our buying time from that. And this is basically without lots of generality, right? You could try to imagine, oh, I have like conditional based on what's happened in the past, right? But because only one thing can happen, right? Either I keep skiing or it stops. I can just draw the full distribution at the beginning, right? It's the same thing. I have some purchase distribution which the adversary knows. It's an oblivious adversary, right? So it doesn't know what the actual draw is from that distribution. And okay, here's like, this is the last solution we talked about, right? Which in this case, I did b is like this 200, right? I buy it time b minus 1, probability 1. So that's a distribution. Fine, okay. Here's another distribution that looks an awful lot like an exponential. It is an exponential. Fine, right? That's another distribution. But I can choose any distribution I want. Right? So I want to wave my hand and make one observation. The actual proof of this is also very short, but you actually need to go through like a minimax type argument, and I kind of skip. But the observation is there's no reason for me to ever put probability mass on time past b. Right? Intuitively, if the adversary, if I do that and the adversary chooses some time past b, right, then the adversary is saying the optimum was to buy at the beginning, right? Because it chose a time past b. So then it wants me to rent as long as I can. So it's actually just going to be forever. Right? If the adversary chooses some time after b, it's actually choosing, right? In which case I know that the adversary is going to choose infinity, right? Or something earlier than b, so I'll just cut off my times at b. Right? Same with the adversary cutting off before b, then I can just move all that mass in the end to b and nothing. So that means I'm going to show hopefully almost all this talk is basically just me pointing my hand and waving furiously at plots that look like this. Right? So I don't have to consider things past that. Okay, so I need to formalize this a little bit about what I actually want. Right? So what is the competitive ratio if I buy at time t and the adversary stops at x? Well, you think about what we just said, right? It's this thing. Right? If I buy after the adversary stops, well, I know the optimum thing was to rent every time, right? Because I never put any mass past b. Okay, so I'm not considering what happens past b basically doesn't matter. Right? So if I buy after the adversary stops, then I rent it every time. That was the optimum thing to do. I have competitive ratio 1. If I buy before the adversary stops, then I bought and I rented for t minus 1 time. The optimum thing to do is buy, so I have that competitive ratio. Fine. Okay, which lets me now write the expected competitive ratio if I choose from this distribution. Okay, and that's exactly what you think it is, right? Sum over all possible things I can choose of the competitive ratio. If I choose that, times the probability of choosing. Okay, definition of expectation. Right, you do the math, and it's this. And now there's very simple math, which is actually turns out to be very crucial for things being nice, which is that this p is a distribution. Right? So if I sum up the probability mass after x, that's just 1 minus the probability mass before x. Okay, so I can write it as this. Okay, and this is very nice because this only depends on time at most x. Okay, so this has this very nice property that if I want to know what happens at time x, it doesn't matter what goes on after it. Right? Choose any crazy distribution you want, it is totally irrelevant. Okay, and now I'm going to do worst case stuff, right? So the expected competitive ratio, if I choose from this distribution, right, the adversary is going to choose as bad a time as they can. Right, maximize x. Okay, we all good with the setup? So this is the classical randomized solution from Carlin et al., which I didn't look it up, from some of you might remember who are older than me. This is actually soda number 1. Very first soda.
Oh, really?
Is this paper. And they showed this is the optimal distribution. Something which is hard to look at and understand what it is, right? But it's some constant depending on B, right? Times something that this which grows depends on B and on T. Okay, so because this is super hard to understand and I don't want to look at things like this, right? We're going to actually move to an easier, more intuitive setup where it's continuous. Right, so one of the other things I teach my undergrads when I teach this is that there's like the elevator waiting problem instead of the ski rental problem, right? Which is how long you hit the button on the elevator, how long do you wait for it, right? Versus take the stairs, right? And that's just like a continuous version of this. So imagine we're doing that. And so I can renormalize time to be 0 to 1, right? So B is 1. Renting for the first T costs T, right? So if I rent for the first half unit, right, then that costs me half. Buying costs me 1. And we can let X and T be continuous. Right? And you kind of see that this is formally equivalent to kind of renormalizing the days to be, instead of 1 through B, it's 0 through 1, but indexed by 1 over B, multiples 1 over B, and let the limit as B goes to infinity. And then P gets me a probability density function. So I'm going to kind of switch back and forth between discrete and continuous, like multiple times, because sometimes it's easier to talk about one than the other, and I'll always choose one that's easier to talk about. And they're morally the same thing, at least when B gets large. In that case, this crazy thing is very simple. It's just the exponential distribution, right? Normalized, so it's a distribution, so it's mass 1 between 0 and 1. This is the optimal thing to do. And that's what Carlin et al. Proved. Okay, right? That's why I showed you the exponential. Okay, so we good with this? Okay. Right, so this has competitive ratio, or expected competitive ratio of E over E minus 1, so about 1.58, right? Which is like notably better than 2, right? Obviously, like, the deterministic thing gives me 2. 1 is the best I could possibly hope for, right? So the whole game is like, what's the constant between 1 and 2? So 1.58 is pretty notably better than 2. Okay, so like we're done, right? That's why no one has studied ski rental since the 90s. We know what the answer is. But okay, so here's the question, like, are we actually happy with this? And Arvind, I think, alluded to this, right? Like, are we happy with a bound on the expected competitive ratio? Does this solve the question to our satisfaction? And it kind of, your intuition about this can depend on your background a lot. So like for me, I never even thought about this for many, many years because my background is in approximation algorithms. In approximation algorithms, expectation is all that matters, right? Because I run at log n times, in sequence, and then I get concentration, right? And that's fine, right? So like we never have to worry about concentration of our algorithm, right? There's pieces of our algorithm that we need to concentrate to prove that our algorithm works, right? But like having bounds and expectation is good enough. But for online algorithms, it's very unclear if that's true, right? The whole storyline here is like, I run this once, it's the worst case. Like, am I actually happy with expectation? And I think the answer would be that maybe you are in some cases, but probably you're not in many cases, right? Like you want stronger bounds on the tail. In particular, you might ask the following question: what's the probability of being worse than 2? Right? Because I don't know, like when I took like CS 101 when I was an undergrad, the professor motivated NP completeness by saying, I want to be able to prove something is NP complete because my boss asks me to come solve something that turns out to be NP complete. I need to go like have evidence that I can't do this, right? Like whole motivation is I don't want to look foolish in front of my boss. Right? And this is actually kind of the same thing, right? Like suppose I run this randomized algorithm and I get a competitive ratio of 3. My boss says, what are you doing, you idiot? Like you could have competitive ratio 2, right? Like deterministically. We're very unhappy with that. Right? So of course I can imagine any kind of threshold here, right? But like 2 is a particularly kind of important one, because that's what you get in the deterministic setting. Okay, right? So we can calculate this. Right, this is the calculation. I know the distribution, especially for continuous setting, right? I said, what if the average is a half? It turns out it's the right thing for them to set, which I'm not going to convince you of, but if the average sets it to a half, you do this computation, you say, well, if I commit to buying at a half, right? And if the average rate commits to ending the time at a half, and I buy before that, then I'm in trouble. Right? Because I paid, at least 1 in order to buy. Right? And opt was a half. Maybe I paid even more because I rented up to 1/4. Right? And I pay at least 1 to buy, opt was a half. My competitive ratio is 2 or worse. Right? Okay, so what's the probability I buy before a half? And do this integral, like 37%. Which, again, kind of depending on your point of view, is that good or is that bad? How scared are you of your boss? It kind of depends. So when we were figuring this out, I was at Google in Sergey Veslovitsky's group. He's one of the co-authors here. And we kind of did this calculation at the end of the day. And his reaction was like, oh, that is really high. Like, this is a very high probability of looking like an idiot. Right? So I'm not super psyched about this. Okay. Okay, so I want to enforce tail bounds. Right? I'm going to have it be this kind of general thing where, like, you can imagine lots of ways of saying I have concentration, I don't look like an idiot, and I want to bound to variance, I want to bound higher moment, blah blah blah. Right? I'm going to have explicit tail bounds. Right? So this says I want probability at most delta of having competitive ratio worse than gamma. Okay, so think of gamma being 2. Think of delta being something, hopefully much smaller than 37%. Right? That's the kind of thing I want to enforce. Right? So here's kind of the main set of questions we ask. What are the optimal solutions? And again, my objective is to minimize the expectation. Okay, my constraint is I don't want to have very high probability of looking like an idiot. This is not the only way of this is a design choice, right? Like there's many other interesting questions that have other versions of this, right? But we're going to try to minimize expected competitive ratio subject to a tail bound. Okay, and you can ask a bunch of different questions. Right? What if I give you a whole bunch of them, right? So I can really control the tail. So you have at most this probability of being worse than 2, at most that probability of being worse than 3, at most that probability of being worse than 4. I could give you this whole set of tail bounds and say, satisfy all of it. I could give you 1 tail bound. I could give you 1 that has a probability of being worse than 2. Or this is another interesting case. I want to say I'm never worse than some gamma. Right? So let's say gamma being 2, I've got a 2-0 tail bound. That's the deterministic algorithm. Right? I know how to do that. We could say, okay, you're allowed to use randomization, but you need 0 probability of being worse than 3. That might be something you want to ask. Okay, so let's gain some intuition by thinking about a single 2 delta tail bound. Any guesses on a natural approach here? I claim based on the 2 things I've shown you, there's at least one very natural approach. Okay, so I have this deterministic thing that is never worse than 2. I have this randomized thing that is sometimes worse than 2. How do I decrease the probability of being worse than 2? Yeah. Yeah, I'm essentially going to interpolate between the deterministic and the random. This is, I claim, kind of the obvious approach if you think about this for a minute. Right? So, good. Right? With some probability, run the classical deterministic. With remaining, run the classical randomized. We calculate what those probabilities need to be given a delta. And you get things like this. So, for example, here's what you get if I want my delta to be 0.19. I get some, thing that is an exponential. It just looks relatively slow growing. When they run it with kind of low probability. And then I drop at the end because I have some pretty high probability of running the deterministic algorithm. This is the natural. And it works fine. This totally does the thing that we want it to do, and it is absolutely better than the deterministic, right? So, like in some sense, we're happy this works. And it kind of has some natural nice properties, right? Like it's monotone, right? That's kind of nice. It really only has this one discontinuity at the end, right? Just like the classical deterministic. It's basically never like 0. Right? There's no times that I just completely give up on.
So, Mike, even that's not a discontinuity, right? It's just a non-differentiable point. Is that what you meant?
It's discontinuous, right? I mean, so in the continuous case, right? I'm really jumping. There's an honest God discontinuity.
Okay. Okay.
But I'm actually, Aravind, you might catch me in a bunch of things. I'm going to use a bunch of technical math words in ways that are not true.
Okay.
I'm going to say things that are hopefully like more true.
Okay.
Good. So good. So this has a bunch of nice properties, and the natural question now is like, okay, is this optimal? Was this the right thing to do? And hopefully you can tell, like, the talk isn't over yet. The answer is no. Right? So our results are basically like the optimal solutions are what? Like, not solutions we would have kind of come up with by thinking about it on base. So I said I got to write code for this because like we actually wrote code to figure out these optimal solutions, and we're kind of flabbergasted when we saw the results. Okay, so what are the optimal solutions? Let's kind of go from maybe less crazy to more crazy. So if I set this type as gamma 0, so this is if I set gamma being 10 and delta 0. This is the optimal solution. So I only have this kind of one weird discontinuity, this one weird jump, but it's not at the end, it's at the beginning. And actually at the beginning I'm 0. And then I jump up to something very big, and then I jump down, and this turns out to be an exponential. You can see in this plot that turns out to be an exponential. That is the honest to God optimal solution. Okay. What about here's a single 2 delta tail path, the delta being 0.19. Okay, like it goes down to 0 like a lot of times. It has these slopes that keep getting bigger when it's not 0. Like, okay, there's a bunch of times like you just run this algorithm. What does it do? It has some probability of buying it early, and you say, nope, it's not going to have any probability of buying in this whole regime. Then I have more probability of buying, and it goes faster. And all of a sudden, like, nope, no probability of buying anymore in that regime.
The
Yeah.
optimum is unique, or
Yes, I'll give you a proof later that it's this is actually a unique optimal. Yeah. Like this is the honest to God unique optimal solution. Okay, something that I think is maybe similarly crazy to this. Let me just show you something with a different value of delta. At 0.31, this is the optimal solution. So this doesn't have as many like crazy up and downs, but instead of just going from like big to 0, big to 0, big to 0, now I have like big to less big to 0 to big to an exponential. Yeah, these are the optimal solutions. So like this is to us the story of this paper, the story of this work, like isn't our proof that these are the optimal solutions or they're unique or this. It's just like I was not expecting the optimal solutions to look anything like this. And I think this is very surprising, right? That we take the simplest of all online algorithms problems, right? Ski rental, something that has been looked at for decades and decades and decades. And somehow, and we think we fully understand it, somehow you throw in this tail bound and all of a sudden, like, it's crazy. Yeah, so that's why this is a very fun project to work on. Okay, you good? Okay. Here's what I'm going to try to do. I probably won't do all of this. I certainly won't do all of this. So first, we're going to try to prove, or at least hand wave, a characterization theorem for this arbitrary collection. So I'm going to give you as many characteristics as you want. And I'm going to give you a characterization theorem that says that, you know, the optimal solution is the unique solution that satisfies these properties. Okay, I'm not going to tell you what the unique solution is. I'm going to say it's the unique solution that satisfies these properties. Okay, that's going to, as a corollary, give us an algorithm to compute this optimal solution. Okay, then we're going to use this characterization theorem for a single gamma 0 tau constraint to prove that this is the optimal structure for a single gamma 0 tau constraint. And this really needs 0, a spike, and then an exponential. That's what it has to look like. And then we're going to use the characterization theorem not to actually explicitly give these solutions, because it turns out actually in the continuous case, you can't express these solutions with elementary functions. So we can prove that you at least need the Lambert W function to express this thing. So I'm not going to actually say this is the optimal solution. I'm going to prove that the optimal solution has all of these crazy properties that it looks like it has. Okay, even when gamma is just okay, good, cool. Right, and like I said, this is I think the story of the paper. Yeah, the story of the result is like the solutions are crazy. The rest is technical stuff, right? That we need to do, but I always get annoyed when like reviewers look at like what is the main theorem that's hard to prove, and they say that's your main result. Like, no, that's not the main result. Like, that's the tool to prove the main result. Okay, so let's actually do some math. Okay, so what does it mean to have a tail bound? It's that I have at most delta probability of being worse than gamma. Right? I claim it means something about the following interval. It is bad interval. Right? So define the bad interval for x, the threshold gamma, I gamma of x. This time, if the adversary stops time at x, what are the times that I'm very unhappy I bought it? Right? The times that my competitive ratio is larger than gamma if I bought it. Okay, so this is instead of t, such that alpha of tx, competitive ratio of I by t, the adversary chooses x, is bigger than gamma. These are the bad times. You do some math, the higher definition of alpha, right? So you do the math, and this is what it is. Fine, it's this. It's the right. So how to interpret this, right? Let's do this math. This is gamma x minus b plus 1, you get a plus 1, right? Large, whatever, right? So for b over 2, this is like 1 to b over 2. For 3b over 4, it's b over 2 to 3b over 4. It's this kind of interval that moves along once you're at a half. So when you're less than a half, when you're at less than b over 2, the interval is 0 until that point. Right? That's what this max is 0 is doing. And once you're at least b over 2, it's this interval that moves along, and the right endpoint moves at half the speed of the left endpoint. Right? When gamma is 2, that's general 1 over gamma. Okay, right? And the point, right, is that if you give me a collection of these, then I satisfy all of them if and only if the probability mass in each of these bad intervals satisfies the tail bound for all x. Okay? And this is obvious, right? If there's some x where it doesn't satisfy it, the adversary can choose there, and by definition, then I have too large a probability of that bad competitive ratio. Okay, so now we can kind of even more formally define stuff, right? I can let P be the set of all distributions that satisfy all these tail bounds. Again, I don't know if Arvin's going to get mad at me because it should probably be like a supermum. I'm just going to call it a max. Fine, right? Of all of, so I care about the expected competitive ratio when the adversary gets to choose the time, but I now have to satisfy all of these tail bounds. Okay. Okay, so here's the characterization theorem. This is like the main tool we're going to use. It says that for every time x, one of the two, maybe both, but at least one of the two is true. Alpha p of x is opt, right? So this says basically, right? Remember, alpha p of x is the expected competitive ratio if I use p and the adversary chooses x, and equaling opt, right, means that if I choose the optimum p, then some of the x's will have this minimum equal to opt. Or sorry, some of the x's will have this max equal to the value of the actual expected competitive ratio, and some will have below. Right. So you can, this is a common thing we do in algorithms, right? Is we have like an objective function and constraint. Then we just kind of like think like, well, suppose I knew the value of the objective function, and let's just like think of that as a constraint. So think about like I know opt. So it says the competitive ratio constraint is tight at x. Right? If the adversary chooses x, then honest God, my expected competitive ratio is optimum. It's no better. Or one of the tail bounds is tight at x. The adversary chooses to stop at x. There's one of my constraints. I am just on the verge of not satisfying. Okay. So if you think about a minute, this should be pretty intuitive. And in fact, this, depending on your background, like a lot of people say, okay, this is going to be obvious from LP duality, which is kind of more or less morally true, but the proof doesn't go that way. Okay, but I claim a corollary of this kind of answers one of the earlier questions. This already gives us a simple algorithm to compute the unique optimal solution. Right? Why? Well, okay, think about this theorem at time 1. Right? At time 1, it says one of these two things is tight, or both. Right? Both, and we did this transformation, right? We said that the expected competitive ratio only cares about times before it. That's why that was very important, right? It doesn't care about what happens after time 1. Right? Okay, like I just think about it as like a water filling algorithm, right? Like I'm adding mass to time 1 until something becomes tight. And you do the math, it turns out it's that P1 there. That's what one of them becomes tight. Then I move on to P2 and I just do the same thing. Right? I'm just go from left to right and I add probability mass until something becomes tight. I never had any choices anywhere, so this is the unique optimal solution. Okay, I will say this is very simple, again, assuming you know opt. If you don't know opt, you can do some binary search thing. It turns out the technicalities of that are like super annoying, so that's a very long appendix in our paper, but it's not like exciting. Okay. So I just go through and for PT, I say, you can do the calculation. This is the slack of my constraint I, this is the slack of my competitive ratio constraint, and, take the minutes. It's watered off. Okay, so how do I prove this? So first we prove this helpful lemma. It says that at the end of time, at time B, the competitive ratio constraint has to be tight in an optimal solution. Okay, and you prove this by saying, if it's not tight, I can move some mass to that, and that can only help. More or less how that proof goes. Okay, so again, I'm going to just hand wave that, and take my word for it, and go look at the paper if you care about the details. Okay, so now I want to use that helpful lemma to prove the theorem. I say, okay, let's suppose it's false. Let me look at the first time, let's say T1, where neither of these is true. Okay, so I've kind of slack in all of my constraints at T1. And then I look at the next time, right, the first time where I become tight again. Right, so maybe it's T1 plus 1, right? Maybe T1 is not tight and then immediately become tight again. Maybe it's later. Okay, so T2 is the first time that something becomes tight again. Okay, and now you can argue that I just move this kind of differentially small or like epsilon amount of mass from T2 to T1. Okay, and if you think about it for a minute, you'll realize what this does is it's not going to hurt any of the elements. Which is not obvious. You have to think about the structure of these bad intervals. And it basically says, why, if I move from T2 to T1, I could be bad if somehow like there was some tail bound, some bad interval that had T1 but not T2, and that was tight. But any such time has to be between T1 and T2, and by definition, nothing is tight for any of those times. So this is still feasible. This doesn't actually hurt my feasibility. Turns out this also doesn't hurt my expected competitive ratio for anywhere. Or at least it can hurt in various places, but because things aren't tight, it doesn't hurt me above opt if I move a small enough amount of mass. Right? And you can prove, again, intuitively, think about what happens time after T2. Right? I moved a little bit of mass from T2 to T1, so I have a little bit higher probability of buying early. Right? For x's that are out here, right, that helps me. Because now there's this tiny amount of probability that said I bought here, right? So I rented to here and then I bought. And now instead of that, I have the probability of renting to here and then buy. Right? So that's better for me. Okay, so actually I'm better for all the times that are out here. Actually slightly worse for the times that are between T1 and T2, but those aren't tight anyway. And then things before T1, you haven't changed it. Right, so this contradicts the helpful lemma, right? So that everything out here I've improved, but if I was previously tight at the end, now I'm doing better than that, right? So I'm below opt, and that contradicts. So it's just this like small amount of mass moving argument and reasoning about how that affects things. So that's the whole proof of the characterization theorem, basically. So now let's do that warm up, that second thing where I have a single, what we call a pure tail bound. So delta is 0. Right? Some threshold, and you're not allowed to violate that threshold with any probability. Okay. So we can make some simple observations. But look, if you're some time and you're in someone's bad interval, then you better have probabilities. Right? Because you're not allowed to violate this tail bound, right? With any probability. So all of these bad intervals have to just be in. You can't have any probability mass in there. Okay, alternatively, if you're not in anyone's bad interval, then in particular, you're not in your own bad interval. Okay? Which means, if you think about what the definition of bad interval is, right, the right-hand side is always you. Right? So if you're not in your own bad interval, your bad interval is empty. If your bad interval is empty, then you can't possibly be tight in that constraint. So the characterization theorem implies that you better be tight in the expected competitive ratio. And that's what it is, right? So at the beginning, for a while, like before b minus 1 over gamma minus 1, you are in your own bad interval, so you better have probability 0. Then at some point, if I got b minus 1 over gamma minus 1, let's assume those divide correctly, right? Otherwise, I have nasty floors and ceilings and stuff hanging around that I don't want to deal with, right? So at b minus 1 over gamma minus 1, all of a sudden, this is the first time that your bad interval is empty. So I know that from then on, the competitive ratio is supposed to be constant. And when you do the math, what that means you have to have this huge spike followed by this thing, which is basically an okay. So yeah, this is the math. It's not like super hard math, but like it's not obvious that the right way to keep a constant competitive ratio is a spike and then an exponential. Like that's not obvious, but that's just some calculations you can do. Okay, and then the theorem, if you do that, is like this is your expected competitive ratio. What is this? Some crazy thing, right? A bunch of B's and a bunch of T's, a bunch of gammas and B's. Okay, but like usual, the continuous case is kind of cleaner, right? In the continuous case, it's just that's your expected competitive ratio in the continuous setting, which is a little easier to understand, hopefully. I can kind of see that when I set my threshold at 2, the best I can get is 2. That's my deterministic algorithm. That's 0 probability of being worse than 2. And then as this goes to infinity, this goes to 1 plus 1 over e minus 1. Send gamma to infinity here, right? Which is e over e minus 1. That's like classical randomized with no tail. Okay, so this behaves exactly as you'd expect. Okay, good. Okay. Let's move on now to this more complicated setting of like a 2 delta calculus. So like I said, this is very annoying. We spent a lot of time trying to figure out like what is it. We realized like we couldn't when we started solving these things and getting these Lambert W functions. Didn't want to deal with that. So that's annoying. And the other thing is that in this setting, there were like 3 regimes basically, right? 0, spike, exponential. And we just saw, I showed you earlier, right, that with a single tail constraint, you have lots of these different regimes, right? They can start growing quickly, they can kind of jump between each other, very strange. So I'm going to try to give you some intuition for what's happening based on the characterization. Okay? And we're going to try to prove some surprising properties, like it's non-monotone, okay? It definitely drops. In fact, it drops to 0, and then goes back up. Drops to 0, then non-0. And I get growth rates that are like arbitrarily large. So in regimes, I can kind of focus in on these windows where it's non-zero. It's in the continuous setting going to be continuous. And its growth rate's derivative is kind of arbitrarily large. Okay, so these are very, I think, surprising properties of the optimal solution. So this is the picture I'm going to just stare at and wave a lot to convince you what's going on. Right, so this top bit, this is my optimal solution, right? I showed you exactly this plot with some helpful orange lines to line things up. Right? But this is the optimal solution. I showed you a few slides back, or delta being 0.31, I guess. Which again, like remember with delta being 0.37 or 0.38, right? Then I just get the classical setting, right? So it's only a little bit better than the classical setting. It's already like totally crazy. And you can hopefully look at this and wave your hands and convince yourself of what's happening. Right, so what's happening? Like I put these orange lines are supposed to line things up. So this plot is the expected competitive ratio. So it says if the adversary stops at this time, and I use this distribution, here's the expected competitive ratio I get. And this is the tail constraint. Right? This says if the adversary stops at this time, and I use this distribution, what's the probability of being worse than 2? Right? So the characterization theorem says basically at all times, one of these 2 things has to be tight. Right? Tight meaning you have this kind of top line. Okay, so what's going on? So at the beginning, especially think of large B or think about the continuous case, right? We know from our algorithm that P1 is supposed to be this thing. And as B gets very big, right, this becomes much smaller. Right? So initially, it's a competitive ratio constraint this time. Okay, and then you can prove a lemma that says to keep the competitive ratio constraint tight, I have to grow like an exponential. So I guess start out like an exponential. Okay, but as I'm growing like an exponential, my competitive ratio is constant, but I'm starting to add mass to these bad intervals, right? So I start getting a higher and higher probability getting this bad competitive ratio, right? And then at some point, I hit my bound of 0.31. Okay, so what do I do there? Well, if you think about it, I have to actually drop all the way down to 0. So why? We'll see this formally next slide, right? But it's because at time half, in this case 100, the bad interval is the whole first half, right? All of these bad intervals actually, right? These are like a laminar family, even more than that, right? Like they're prefixes. Right? So once I hit delta mass in this prefix, I have to be down to 0 until time half. Okay, and then all of a sudden at time half, right? Now my tail bound is, or my tail constraint is not tight unless I add mass, right? So I add mass according to my algorithm, right? Until something becomes tight, and I'm keeping this tight, and I'm able to add mass like pretty quickly, and we're going to figure out exactly how quickly, right? Then my competitive ratio, because I'm adding mass, goes back up until at some point that becomes tight, right? And then you can kind of see how this plays out, right? This is kind of, I'm always adding mass until one of these becomes tight, and then that means the other one starts dropping. Right, so there's some people who know a lot more math than I do, probably know that there's some word for this, which I don't know, but it seems like some kind of like dynamical system or something, right? As I'm evolving and I have these constraints that are becoming tight, blah, blah, blah. So like at some point we just showed like these plots to Bobby Kleinberg and asked like, hey, can you help us like figure out like the actual equations for this? He's like, there's no way you're gonna be able to do that. Dynamical systems are too complicated. Fine. So, okay, this is complicated math. Okay. So that was for this. This is actually a particularly complicated setting because of this drop from this function down to this thing, right? So I want to actually be in a slightly easier setting to begin with, which is the setting where optimum looks like this. This is a different plot I showed you at the beginning. This is for smaller delta. I can't read what it is. What is that? Smaller delta, 0.19. Okay, so what am I going to do? Okay, so first I divide into these special intervals, which are things we all like, because we're all computer scientists, we like powers of 2, right? These are 1 to a half, half to 3/4, 3/4 to 7/8, 7/8 to 15/16, right? Like, okay, these intervals. And these are nice because these are exactly the bad intervals for the right endpoint. Right? So when you go back to the definition of bad interval, the bad interval for time half is this whole interval P0. The bad interval for this time, which is time 3/4, right, is this interval P1. The bad interval for time 7/8 is this interval P2. Okay, so that's some nice things. We like powers of 2. Okay, so I'm going to prove the following lemma, which is very easy because we kind of already did it in the last slide. That at the beginning, in this first setting, for P0, you're an exponential, then you're 0. Right? We basically just did that in the last slide. Right? You have to be an exponential to start out to keep the competitive ratio tight, and you have to drop to 0 once your mass constraint becomes tight, then you're 0 until all of a sudden you have freedom to add mass again. Okay. Okay. Now this is the useful lemma, which is going to make this setting easier than the last one, is that once I set delta small enough, so some function of I, small enough function of I, it's basically 1/6i, care about the constants, I can assume without loss of generality that the expected competitive ratio is not tight anywhere in this PI interval. Okay, so I get a picture that looks like this, right? It's always trying to get back up to the competitive ratio, but it never can, right? Until after the ith interval. So which delta I need? So if you fix I, saying, okay, I care about the P4 interval, then I can set delta small enough so that's true of P4 and of everything before P4. Okay, so again, I'm not going to prove that to you. You can just kind of look at the graphs and kind of convince yourself that seems plausible. You can do a proof of this. Right, but now my characterization theorem means that if the competitive ratio isn't tight anywhere in here, then the tail constraint has to be tight everywhere. Here's the lemma. I'm also going to say a bunch of like mathematically false things that are morally true, hopefully. and abuse continuity in places. I claim that PT has to be 2p2 minus 1, where t is inside this pi. So why? So okay, you can do the math, but like intuitively, think about what's happening, right? I said this bad intervals, right? The right endpoint is moving along at half the speed of the left endpoint, right? So if the mass constraint is tight here, and then I move a differentially small amount to the right, right? Then the other endpoint moves twice as much. And this is supposed to be tight, right? Both those intervals are supposed to have delta mass. So I have to add exactly as much mass as was in these like 2 time points that I lost. Right? So that's what this 2 is. Right? And that's what, so 2t minus 1 is just, in the continuous case, the left interval of the left endpoint of my bad interval. Right? That's what's going on. She's saying, look, if you're tight here and you're tight at that plus epsilon, right, then you had delta mass here, you have to have delta mass there, you just have to add in whatever mass you lost. Right? That's all that this is doing. Okay. Now this thing I want to prove about general PI says that in PI, you grow like e to the 2 to the I. So these increasingly steep exponentials. Right? That's what's going on here, right? That's a single exponential. That's e to the t, that's e to the 2t, that's e to the 4t, that's e to the 8t, that's e to the 16t. Normalized in some constant, which is going to depend on that. And then it's going to drop to 0. That's what the PI interval has to look like. Okay, proof sketch. I do induction on I. We just proved this for I equals 0. Let's do this inductive step for I. So it's true for I minus 1. Well, if I give you some time in PI, then I'm not going to do this calculation, but convince yourself of it. The left endpoint, right, of that interval, that 2t minus 1, and that's in PI minus 1. Just the definition of PI being these powers of 2 intervals. That means that kind of for t early enough, right? So starting, let's say, at the beginning of P2 and then kind of for a while, that 2t minus 1 lies in this thing that before was by induction, an exponential with some equivalent exponent. Okay, so by induction, Pt is 2t minus 1. So my induction is equal to that. Right? And now I left out this 2 to the I minus 1 times 2t. I get 2 to the I times 2. Right? And then this extra 2 to the I minus 1 drops down to the constant. This is a very straightforward calculation. And then at some point when t is later, right, then 2t minus 1 is in the 0 regime earlier, which we know exists by induction, right? And so I have some 0. That's the sketch.
And by the way, what's happening in that very, very last interval?
Yeah. So good question, because it's actually, so the answer is, okay, what's the answer? The answer is, with this value of b, right? This is not continuous. This is us setting b to like 2000 or something like this. In this interval, the competitive ratio constraint is tight, and so you're in exponential to keep it tight. So you always actually end, right? So we had this helpful lemma that said at the end, it's always the competitive ratio constraint that's tight. Turns out when you discretize even a little bit, turns out at b minus, so both b minus 1 and b have empty bad intervals. Right? So as b goes to infinity, in the continuous case, this doesn't show up, right? But b minus 1 and b both have bad intervals. And so at the end, or with empty bad intervals, so at the end, you will always have the competitive ratio constraint being tight for both b minus 1 and b, which means that there has to be this exponential relationship between at least these 2 points. Here it's more than 2 points, because in this case, you actually hit the competitive ratio constraint and got to stay there, right? So the other way to think about it is in this middle plot where you're plotting expected competitive ratio, as these get steeper and steeper and steeper, you get to increase the competitive ratio faster and faster and faster. So at some point, you get to increase it fast enough that you actually do get to hit that top again. Right? And then you're going to shift just to an exponential until you run out of mass. And in this case, you never run out of mass. So here, I think this was for delta being 0.19. If I showed you the same thing for delta being like 0.01 or something like this, then you have just like this huge, huge number of spikes, right? And this kind of ending exponential is kind of arbitrarily small. Does that answer your question? Okay, so kind of the whole message here is like we had to do some proofs. They're not like the most complicated things in the world, but they needed a couple ideas. But really kind of look at these plots and they tell you what's happening. Right? We just need to prove that then we actually do have these crazy solutions. Okay. So to sum up, right, ski rental, most basic of all online algorithm problems. If you asked me 2 years ago, is there anything unknown about ski rental? I would have said no. Especially if you'd said, is there anything natural and unknown about ski rental? I definitely would have said no. But we had these very normal tail constraints involving, not looking like an idiot in front of your boss, right? Not being worse than deterministic. And all of a sudden we get these solutions that are just like completely weird and crazy and very hard to interpret, right? Like people talk about interpretable machine learning and neural nets and stuff. Like, how am I supposed to interpret this having a 0 probability of buying it for like right here, but having non-zero probability before and after? It's just weird, even though you can do the math and it's true. Okay. Open questions. Okay, so I started out talking about this interpolation. It's obvious that if I take the deterministic and I take the randomized and I just interpolate between the two of them, you can plot what that would give you for expected competitive ratio as opposed to the delta. Let's keep gamma being 2 here. That's a 2 delta tail constraint. And then this is what we get. This blue is ours. Okay, so we're notably better at certain places where we're really not better. But there's still kind of a lot of stuff we don't understand. And I want to point out these 2 things. Okay, so one thing is that representing the optimal solution, you can't do with elementary functions. So like in my view, semi-hopeless because I'm not a good enough mathematician to be able to try to use fancy functions to represent this. But that doesn't imply that you can't write this curve, right? The value of the optimum as a function of delta. That might be a simple curve for all I know. We don't know how to do that. I don't know how to write that. So like say, this is the expected competitive ratio you get. So that's a great open question, figure that out. Similarly, right, this curve looks awfully continuous, right, when you plot it, right? And yet you can clearly see that there's these weird kind of quote unquote discontinuities in the structure of the optimal solution. So look at these 2 points. This is delta being 0.18 and 0.19. Right? So like very close points on this curve. And for 0.19, I have like 1, 2, 3, 4, 5 non-zero regimes. And for 0.18, I have 1, 2, 3, 4, 5, 6 non-zero regimes. Right? So there's like an honest to God discontinuity in the structure of the solution. But that discontinuity doesn't seem to be affecting the value of the optimal solution. So I don't understand what that value is, right? Or how it's continuous, or proof that it's continuous. It just looks like it. Like understanding this curve is like the main interesting open question here. Besides what we actually think is like, what we finish our paper with, like the big open question is like, look, ski rental is the most obvious online problem, right? There's this whole decades of worth of other online problems. So, if tail bounds in ski rental is this crazy, like what do tail bounds look like in like metrical task systems, right? Or, whatever your favorite online algorithms problem is. So hopefully, fingers crossed, knock on wood, someone, maybe people here, like get very excited about this and start proving things about more complicated online algorithms, and we get, a whole bunch of cool results on concentration bounds or tail bounds of online algorithms. Okay, thanks.
Thanks a lot, Mike. Let's thank Mike. So I have a question, and of course, others feel free to ask. So one natural question, of course, is given the recent interest on algorithms with predictions, and of course, you also have worked on this, Mike. Are there maybe weak assumptions we can make on the distribution of the adversarial solution that that can make the problem more tractable?
Okay, so in this setting, right, we think of the adversary as being like truly adversarial. So if you it's unclear to me what kind of limitations you would put on that, right? Like you could say he's not allowed to stop me too early. Like, okay, people have looked at ski rental with all sorts of extra assumptions, right? Those are all reasonable. People have looked at, like you were saying, Arvin, people have looked at ski rental with predictions, right? So you could think of it's adversarial, but maybe, my adversary is just some person or some computer program, or it's, God giving me the weather, right? It is something. right? So I can maybe learn from past behavior and, figure out what I expect it to be and use that as like a guess. And then you can ask the same predictions question that we ask with algorithms with predictions, right? Like if my prediction is good, I want to do well. If my prediction is bad, I want to not do much worse.
Mhm.
But now you can start adding tail bounds to that. It's a totally reasonable thing to be doing. Yeah, there's a couple papers on ski rental with predictions, and none of them give tail bounds. You could just plug in this same question into that.
Yes, yes. My impression indeed was that those papers only look at expected competitive ratio. Yeah, okay, very interesting. So I had one other question. So this I know less about. So there is this old paper by, I think late 1980s, early 1990s by Ben David, Borodin, Karp, Tardosh, and Wigderson on subtleties about the adversarial models in online algorithms. So yours is an oblivious adversary, right?
Totally.
So I think they show other surprising things. So I mean, oblivious adversary seems the most natural adversarial model. But take a look at the paper.
Yeah.
They have other adversarial models, and they showed surprising sort of contrast between those. So there may be something interesting there.
Yeah, I'll definitely take a look. That's a good suggestion. My kind of high level impression is that for ski rental, there's not a lot of interesting adversaries other than like oblivious and just truly adversarial. But as soon as you start hashing or K-server or metrical task systems, there's lots and lots of different interesting adversaries with different behavior.
Mm-hmm. Mm-hmm. Sounds good. Other questions?
I'm just curious, how many so with these graphs, these plots with the changing deltas, have you computed or maybe would be able to compute many of these graphs and sort of animate so we can see like a visual of like how these plots change as delta increases?
Totally. So I was saying earlier, this is the first time I've written code in like 8 or 10 years or something, right? So like I was on sabbatical, so I had much more time than all my co-authors, right? So I had a lot of fun actually writing a lot of code to do all this. My ability, this is like the limit of my like Python programming abilities, basically. But yes, it takes not too long to run these somewhat depressingly and for reasons I don't understand. So I was at Google and running this on Google Colab, like internally. The internal Google Colab was slower than the external Google Colab, which is slower than me doing it on my laptop somehow, which I don't understand how that can be true, but it seems to be. But yeah, I could solve these for, you plug in maybe 500 days. Like you need B to be large enough to see kind of the tail down behavior, right? But you plug in 1,000 days, plug in a value delta, you can solve this in like a second-ish. So yeah, it's fast.
Are these are for the 2 delta case?
Yes, all these graphs for the 2 delta case. I mean, what happens for larger values than 2 is basically, if you think about it for a minute, you'll see that the bad so at 2, the bad intervals kind of start becoming empty once you're like at B minus 1. But like when I'm at 3, the bad intervals start becoming empty at like a half. Like the bad intervals kind of start becoming empty at like 1 over gamma minus 1, basically. Right? So what they look like is this exact same graph compressed to the first half, and then just a straight exponential. Yeah, what do these look like? What I didn't write code for, and what would be interesting, but I didn't do, is like, what if we have this characterization theorem, which works fine when you have multiple tail constraints. Let me throw in 2 different tail constraints and see how they interact. And we haven't done that. I don't know. Wouldn't be hard to do, I just haven't done it.
You know, the sabbatical.
Yeah, exactly. Exactly. Okay, thanks.
Thank you very much.
Thanks, folks.